Today we're going to talk a little bit more about probability. We're also going to talk about something called sample spaces. Now, I have a hidden spinner. I'll show you the spinner in just a second, but it's not going to show you what colors are on it or even how many colors there are on it. Your challenge is to predict what the spinner looks like without ever having seen it. I'm going to spin the spinner and announce the result each time. Use the space below to keep track of colors and the number of times each is spun. All right, so let me go to my spinner. All right, I'm going to spin it, and it's purple. Keep track of this. Do you know enough right now to be able to tell me what the spinner looks like? No. All right. Let me spin it again. It's orange this time. All right, I'm going to spin it again. Oh, do I have enough information now? Is it half purple, half orange? We don't know yet. All right. It's purple again. At this point, do I know for certain that the purple is bigger than the orange part? Maybe. Don't know. All right, so I've spun it 3 times. And then it's orange again. I'm going to spin it again. It's orange again. Now it's suddenly green. So you want to keep track of how many of each color. So let's make sure everybody's on the same page so far. How many purple have we had? 2. How many orange have we had? 3. And how many green? Just 1. All right. Do you feel like you could draw what this looks like right now? Well, I'll tell you what, let's do it more. So that was 6 times, right? Let's do another 6. See if that changes your mind. At this point, what would you guess? Orange is biggest. Orange is half.
Purple is like 40% and green is like 10%.
Well, how many times have we spun it?
6.
6. So like 1 out of 6, that's 16 or 17%. And 2 out of 6 is 1/3. So like 33%. All right, let's do it another 6 times. Are you ready? We're going to go a little faster. Green. 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 Orange. Purple. Purple. Did that suddenly change how you might feel about it? All right. So that's 12 times. We're going to do this a bunch of times. No. We'll do it 48 times. So far we've done it 12. Are you ready? Okay. Green. Orange. Purple. Green. Purple. Green. All right, so that's 8. We're up to 18 now, right? Green. Green. Orange. Purple. orange, and green. So is that 24 at this point? All right, so again, let's double check. Barrett, tell me what numbers you have.
Purple has 7, orange has 7, and green has 10.
Is everybody on board with that?
Yes, sir.
Okay. So at this point, does that greatly contradict what we thought it was at first?
Okay, so 10 green, 7 orange, 7 purple.
All right. Let's go faster through the next. So we have 24 so far, right? Let's go a little faster. Ready? Orange. Purple. Purple. Green. 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 Orange. Purple. Orange. Green. Purple. Orange. Green. Green. Orange. Purple. Purple. Green. Purple. Orange. Purple. Purple. And green. Check with the people around you and see if your numbers agree with them, and make sure that I've done 48. Done 48? Thank you. So again, check with the people around you if you have not already.
This kid did the hard thing, bro.
16, 13, 19. Bro, I didn't know we were 16.
Oh.
I didn't know what you said. What are they?
I got 13 orange.
16 purple, 13 orange, 19 green.
Yeah.
I can't even count this.
All right, so
How many purple? 16 purple, 6. Oh no. 6. How many orange? 13 orange. 13 orange. Oh yeah.
Wait, how much is green? Green has 19, orange has 13, purple has 16.
all right, so do we have a consensus from the class? There's still some disagreement? All right. So somebody raise your hand and tell me how many purples. Yes, ma'am. 16. And then orange? 13. And green? 19. So if we were going to try and figure out how to divide up the spinner, let's make sure this adds up to a total of 48. So for the purple, how much should we color in purple?
Like less than green, but more than orange.
Well, it would be 16 out of 48, right? That is our experimental probability. 16 out of 48, that's 1/3. Now for orange, it's not going to be nearly as nice. It's 13 out of 48. That didn't come out to be a really nice answer, and that's okay. That happens especially when you're doing these things experimentally. 13 out of 48, let me give you that as a percentage. It's 27%. So it's a little bit more than a fourth. And then green is 19 out of 48. Is about 39.5%. And this 1/3 is about 33.3 repeating percent. That shouldn't be approximately, that should be an exactly. They're all pretty close to one another, aren't they? Relatively. Orange is the least, though. All right. What would make you feel more confident about how we divided up our spinner? What would make you more confident about how we did this spinner? You have a thought?
You go across. You put a line down.
Oh, no. About our numbers. What would make you more confident about our numbers here? Yes.
Maybe like average it around 33%.
Maybe do what? I'm sorry?
Average it.
Average what?
The numbers we do.
Average these three numbers?
Yeah.
Well, they would all come out to be, since there's three of them, the average is 33.3%. You know, when we did just a few, were you very confident of how it was going to look? Okay. What if I did this 500 times? Do you think that the experimental would start to line up better with the theoretical? All right, you guys ready to see what this actually looks like? It's actually half purple.
That seems to happen a lot. One that covers the most surface did not.
I'm sorry?
Seems to happen a lot. The one that's always has the most surface doesn't have the most percentage.
It didn't turn out that way with our experiment. Did we get one of the numbers right?
Yeah, we got.
Green is 1/3.
Oh, green, that was pretty close. Green is about a third, but we were way off on the other two. But if I did this hundreds of times, it should get better. Yes, sir.
At the beginning, we all thought purple was like half blue.
Yeah,
And we had like
actually, at the beginning, we were right on the money, weren't we?
It's more accurate at 7 than it is at like 48 if you like add the percentages.
In this case, yes. Do you think that generally happens? No. Generally, the more experiments you do, the closer you get to the theoretical percentages. All right. So, on the actual spinner, what percentage was orange, or what fraction was orange? Well, let's look again.
13, 48.
No.
Oh,
On the actual. Let me show the subdivisions and it'll be easier to see. This is divided into 6 parts, and 1 part is orange. So that would be 1/6. All right, so the probability of it coming up orange is 1 time out of 6. So how many times would you expect it to land on orange if you only spun the spinner 6 times? Once. How did you get that? There's,
Because there's 6 things.
yeah, there's 6 of them,
There's 6 sections.
and you spun it 6 times, you would expect one time it would land on orange, right? What if you spin it 48 times? It would be what?
8 out of 48.
Yes. Why 8 times?
Because I connected 6 to 48 and then I connected
Okay. So if we have 1/6, if you multiply that by 8 over 8, that gives you 8 over 48. So 8 times out of 48, we would get an orange if it worked exactly. Now, for this one, it's a little bit harder to do it that way because will 6 go evenly into 100? No. Let me show you a way that we can do all of these the same way. Rather than, I did this one this way, and I thought about this one this way, and I thought about this one this way. What's the probability of getting orange? 1/6. How many times do we do the spinner? 6 times. Multiply it by 6 over 1. Here, we had 1/6 times. We're going to spin the spinner 48 times, so that's 48 over 1. That's 48 out of 6, or over 6, which is equal to 8. So let's do the same thing on this one. 1 time out of 6 times 100 times is 100 over 6, which is 50 over 3. That's not going to be a whole number, is it? It goes in, what, 16 2/3? So, do you expect it to come up to be orange 16 2/3 times? No. I mean, that's kind of silly, right? Although, and if you take my statistics class later on, we actually say that 16 2/3 is the expected number, even though it's never going to happen. So, on this, to answer the question, I would say about 17 times. Or if you wanted to say 16 or 17. Okay? Yes, sir.
I did 100 times a different way. I did 6 divided by 1, and then I multiplied the portion, the answer for that, by 100.
Wait a minute, you did 6 divided by what?
And then
6 divided by 1?
yeah, and then I got
And that's 6.
I got a decimal.
Whoa, 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 whoa. 6, wait, 6, whoa, hang on just a second. 6 divided by 1 is 6. Do you mean 1 divided by 6? Okay. So you changed 1 over 6 to a decimal and then multiplied that by 100?
Yeah, and I got 16.6.
And it's the same thing though, isn't it? Yeah. All right. No, that's a good way to do it. You accidentally set it upside down. Cool. All right. Let's go on. Page 2. So I got this problem out of your book because it makes me laugh. Rachel and her little sister Christy also often argue about who should wash the dishes at home. Rachel suggests that they flip coins to solve their argument. Okay, flipping a coin is fair since heads and tails each have an equal chance of happening. Each one has a probability of 1/2, Rachel says. If the coin shows heads, then I do the dishes. If it shows tails, then you do them. Is the system fair? That is, does each girl have an equal likelihood of washing the dishes each day? Is it fair?
Theoretically.
Yeah, theoretically, it's absolutely fair. Yes. The probability for heads is what? Well, let's do it as a fraction. What is it? 1 out of 2. And why is it 1 out of 2?
Because there's only two sides.
Right, there's two possibilities, heads or tails, and the one that we want is heads. That's the way you always want to think about these. How many possibilities are there, and how many desired outcomes are there? All right, probability for tails is what? 1 out of 2. Here's where the trouble starts. Rachel and Christy flip a coin every evening for the first week. Christy has washed the dishes 4 times and Rachel has washed the dishes 3 times. Christy tells Rachel the system is not fair because Christy has done the dishes more often than Rachel. Is Christy right?
Not really, because it's only 7 times a week.
That's
So
odd.
one of
Yeah.
them-
It's not even possible to do the same number.
It's exactly right. You would expect that they would have each done it 3.5 times, but that's not possible.
They help each other on Sunday.
Oh, maybe that's a good solution.
Or the parents do.
So no, Christy's not right. It is a fair system.
I mean, it's working good for them, because, like, if you really look at it from 7 days, it's actually
Yeah,
best it
it's
can be.
it's as good as it can be. Here's where it gets really bad. After the second week of coin flipping, Christy has washed the dishes 10 times and Rachel has washed the dishes 4 times. Now Christy's really mad because she has washed the dishes so many times. In light of the information, do you think the system is fair or not fair?
It's still fair.
It's still fair.
It's still fair. What would you tell Christy? Let me get a volunteer for this because otherwise we'll have too much. Yes, sir. You can tell her womp womp. You have volunteered a lot today. Let me get some other people involved, but I appreciate it. Yes, Ben.
Tough luck.
Okay. I'm trying to convince her not to beat up her sister over an unfair system. Yes.
That there's nothing she can do about it.
Okay. Yes?
Sucks to suck.
Okay. Let's do something that's actually helpful. Yes.
Deal with it.
Oh my god.
Why?
Because it's fair.
Okay. Barrett?
Life isn't fair.
Oh, goodness.
How do you use it?
You guys are kind of missing the point. I'm trying to convince her that this really is fair. Yes.
From a theoretical standpoint, it's 50-50 chance.
Okay. So here's the deal. Although it's kind of one-sided now, what should happen in the long run? It'll even out. In the long run, the numbers should even out.
Maybe one time the older sister will do the dishes non-stop for 2 weeks.
It's possible. It's not very likely, but it's possible. All right. So, if you think about you will think about theoretical probability more in parts 1 through 5 below. It will help if you know what a standard deck of 52 playing cards looks like. I wrongly assumed when I first started teaching this class several years ago that students all knew this. And I had parents that were mad at me. My daughter's never picked up a deck of cards in her life, and I'm like, I'm sorry that you have neglected that part of her education. I didn't know what to say. So here's what a deck of cards looks like. So there are 4 suits. The 2 black ones are, this is spades, this is clubs, or as some people call them, puppy tracks. It looks a little bit like a puppy's footprint. A 3-toed puppy, but
It's my grandma's dog. He's missing a toe.
and then there are red suits, hearts, which look like hearts, and diamonds, which, okay, that's pretty easy. All right. Each suit has 13 cards. The numbered cards are 2 through 10. Then there are the face cards, jacks, queens, and kings. Why there's not princes, I don't know, or princesses, I don't know. Historically, there's bound to be a reason for it. And then there's also the ace. Shh. The ace is not a face card because, well, it doesn't have a face on it. Because I'm looking at it right now. It doesn't have a face on it. All right? So it will also be helpful to know that a standard number cubed, also called a die, plural of which is dice, has 6 sides. Each side has a different number of dots, 1 through 6. All right. So let's look at these situations and decide if you can find the theoretical probability for each one. If you can find the theoretical probability, do so. Okay. I'm going to let you work with the person who is sitting closest to you side to side. Ben, I'm going to make you get to pick. You can be in the group behind you or the group in front of you, either one. All right, no, directly side to side. Okay? Some people are pointing like it's someone way across the room. Paul, you're with Barrett. Got it? Okay. All right, so I'm going to give you a couple of minutes. See how many of these you can find. Go. Whoa. Side to side, dude.
Oh, side to side.
Okay, so
Do it by myself.
you guys are partners.
Mr. Davis, Ben Johnson can work with us.
No, he said.
It's fine.
He said
It's fine.
Let's
Go.
do it by myself.
Let's go.
It's like this is work.
See how many of these you think you can figure out.
Number 2 is, so there's 5, 6, so there's 4 aces, so it could be like, you have a 4, top 5 things, or do we have
Yeah.
anything below it?
Just do those top 5.
Oh, so 6 is.
All right, let's see how you're doing. So for number 1, picking an ace from a standard 52 card deck. So I know that there's 52 total. How many aces are there? 4. Did y'all reduce it?
Are we supposed to?
Generally, we always reduce fractions. It's 1 out of 13. Picking an odd numbered club from a standard 52 card deck. So let's see, there's 52 cards.
52.
Odd, that's 3, 5, 7, and 9, right? So there's just 4 of those. Oh, that's,
No, it's a club. It's specifically one suit.
yeah, an odd numbered club. Now, if it was an odd numbered card, it would have been 16 out of 52. Not rolling a 3 on a standard number cube.
1 6.
No,
5 6.
5/6. Read carefully. It says not getting a 3. Number 4, it's a little strangely worded. But the chances of a thumbtack landing either, and this is with its point up or with the point pointing to the side. Is there any other possibility? I suppose it's, can it, so that it actually stuck into the ground? There's 2 possibilities when you have a regular thumbtack. Either it points up or the points to the side. The probability is 1. It's going to be one of those 2, isn't it? No. Here I'm doing both, point up or on its side. If I asked what's the probability of it, what's the probability of being point up, you might say it's 1 out of 2. But I actually think it's probably less than that.
Couldn't it land on the point though?
No. I mean, if you throw a thumbtack, if you just, chuck it, right, it's not going to go unless you're on something really soft. All right, the chance of getting 1 red crayon from a set of 8 different color crayons. 1 out of 8. Okay, so last thing we're going to talk about today is the sample space. So if you want to have the best chance of getting a red gumball from a gumball machine, is it better if the machine is full of gumballs or half empty? Or does it matter? It may not matter. It may matter, but it may not. Okay? How do the chances of getting an ace and a deck of playing cards change if you have 3 or 4 decks? So if you shuffled 4 decks together, does your chance of getting an ace change? There are more aces, but there are more other cards also.
It's like times 3 or something.
Yeah, it doesn't change anything. Your odds will remain the same. So, in this lesson, you'll think about the size of the sample space, which is the collection of all possible outcomes of an event. So let's pretend you have a bag containing a set of colored blocks with 1 yellow, 2 red, 4 green, and 5 blue. That's a total of 12. Further, pretend that every student has received a bag that's identical to yours. So, you reach into the bag and select 1 block without looking. What's the probability you're going to get a red?
1 and 12.
Try again.
Oh, no.
2 and 12, or 1/6. Green? 4 and 12, which is 1/3. Blue? 5 out of 12. And orange? 0. There weren't any orange blocks in this. Okay, do these answers represent theoretical or experimental probabilities? Theoretical. We are just thinking about this, not actually pulling the blocks. All right. Your homework is in the book. Y'all have a good evening, and we'll talk about this last little bit tomorrow, right at the beginning of class.